Hey everyone, let's try to solve minimum edge weight equilibrium queries in a tree. So in this problem, you are given an undirected tree with n nodes with label from 0 to n minus 1, and you are also given an integer n and a 2D integer array edges of length n minus 1, where each edge have a source and have a destination and also has a weight. Then you are also given a 2D integer array queries of length m. Each query will have two integers a and b. For each query, you need to answer the question, what is the minimum number of operations required to make the weight of every edge on the path from A to B equal? And in one operation, you can choose any edge of the tree and change the weight to any value. So let's take a look at the example to illustrate the idea more. Okay, let's take a look at the first query again. 4 to 6th. We will go through 6th, 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 and 6, 6, 4, 6th. Notice it is kind of obvious that we always want to pick the maximum occurrence of the whole path, which is 6th. So to answer the question of query AB, this is a very simple formula that we can follow, which is the total length of AB path minus the max frequency of all paths. So in here, the total length of AB path from 4 to 6, 4. And then the maximum frequent weight of all the paths is 6, which has the frequency of 3. 4 minus 3 will be 1. So that's why we should output 1 here. So the formula will look something like this. Query AB equals to path length AB minus the max frequency of AB. This will give us the answer of each query. Now the question is, how can we calculate the path length AB and the max free AB easily or efficiently? So let's just take a look at the path length AB first. Obviously, we can brute force iterating every possible node, and for every possible node, go through every other possible node to see how many steps for that source node to the other node. So basically, we are running a nested for loop to check for the distance for each pair of node. Can we do better? There is a concept called LCA, frequently used in tree problem, which stands for lowest common ancestor. So for example, the LCA of 5 and 4 is 2 because 2 happens to be the lowest common ancestor of 5 and 4. And for 5 and 0, the lowest common ancestor is 1 because the first common ancestor of 5 and 0 is 1. So you might ask, how does that help us answering our question? So now if we just choose an arbitrary node as the root, for example, I will choose this one as the root, and I will get the depth every one is the root. So this one will have a depth of 0, and this will have 1. We'll have 1. So now if we want to know the path length from 5 to 4, first we can know the path length from the root to 5. Second is we can the path length from root to 4. And notice this path is not necessary when it comes to calculating the path length from 5 to 4. If we can calculate the LCA first, for example, the LCA of 5 and 4 is 2, then we will know that this portion is double count, and this portion is exactly the cost from root to the LCA itself. So what I'm trying to say is that cost from A to B, the cost from root to A plus the cost from root to B minus the cost from root to LCA A, B, and then times 2. So that's how we can calculate cost or the path length from A to B efficiently. We can do the similar thing when it comes to calculating the frequency, because in a frequency constraint there will be only 26. So each frequency will be the frequency from to A plus the frequency from root to B minus the frequency from root to the LCA of A to B times 2. So from that we can calculate all the frequency, which will be 26 of them, and also calculate the cost, and then we can get our answer efficiently for query A, B. But now the question remains how to find this LCA efficiently. So there is a concept called binary lifting, which will help us to cave parent of certain node fairly quickly. So for example, if the root is 1 and the node is 4, when k is 1, then I want to get its first parent, then it should return 2. And if the node is still 4 and the k is 2, and I should return 1 because it is the second parent. So binary lifting means that we treat the problem in a simpler problem. So that simpler problem is says get parent of p power, node, and then power. This means that I want to get 2 power parent node. So why do we frame this problem in such a weird way? Because this will help us catch the subproblem easily, or to apply DP more easily. So what I mean that, so maybe I will write in here so I have more space. So get parent power of node and pow is just equals to get parent pow of node power minus 1 will get us halfway through our answer. So what we want to do is to apply this whole thing again, but not to ourselves, but to this immediate result. So we're gonna parent power. So the first argument is our halfway through result, and then we will just do power minus 1 here again, and it will give us this get parent power completed. Of course, we have to implement the base case. When the power is 0, you just return the parent of the node, and no need to do it recursively. But once we have completed this helper method, and by the way, this helper method will not be n squared, because the largest power it can go will be the logarithm of n. So roughly log 2 of n, the limit of this power. So in total, this will just run in n log n. And after we have this get parent power, we can solve this cave parent pretty easily, because k will be just some number like 10, 10, 10, 10, 10. We can just treat the k as a binary number, and we apply this get parent pow when the bit is turned on. So that's how we can implement this get k parent efficiently. So once we have this get k parent efficiently implemented, you might ask, how is it going to help with our process in calculating the LCA? So if we want to check the LCA of this and this, the first thing we're going to do is to check the level is equal or not. Level is not equal, then I will just move the one with higher depth x times, where x is the different depth of these two nodes. So let's say that I move it to here, and then the best jump that we can make, which will be the depth of A or B, which in this case will be the same. So you can see after a certain point, all of this parent will be the same. So I can move k equals 1, where k is the time that we move. After a certain point, everything will be the same. So if I apply get the k parent of this node, and we'll go to here, and get the k parent of this node, and will be here. And then if they are the same, then I'm just going to mark their common ancestor in here. Then I want to binary search the lower part to try to search for the first common ancestor when I go through this path. So the first common ancestor is the lowest common ancestor by definition. So that's why we can combine binary search with binary lifting to help us find this LCA. And once we have this LCA, and we can quickly calculate the cost from AB and the frequency from AB, and we can answer our question. And I hope that's not too complicated, and let's jump into the code. So I'm gonna skip some code implementation for basically the part where I implement the binary lifting for getting the k parent, which we're gonna use later. One key component of the whole function is this recursive core, where if p equals 0, then it just means that I need to get this cur 2 to the power of 0 parent. It means that it means immediate parent, so we can just do the base case here. Otherwise, we can do it recursively. The first argument is we go from the current to the halfway through, and then after reaching that node, and we do the similar thing again. That's how we're gonna solve it recursively, and we do this LRU cache, and we can apply the DP, so the whole thing just runs in n log n. And the second thing that we did here is converting the address to adjacency list, which is usually more useful in a lot of cases. And for the parent, it means what is the parents of each node, and the depth means if we treat the node 0 as the root, how many steps does it take for the node 0 to reach that particular node? And for the frequency, it means the frequency from root to a certain node, where the root is 0. As mentioned, there will be only 26 of them, so but it's in one base, so I'm going to pick 27 here. So with that out of the way, then we can start implementing our solution. So first we're going to write the DFS function with first argument as current and the second argument as parent to help us to fill the parents and the depth and the frequency that we're going to use later. So the parents, the current is just a parent. Parent is not equal 0, then depth of the current is the depth of the parent plus 1. So if the parent is 0, which only happens when the current is the root. And then we're gonna iterate every neighbor. So if the neighbor is a parent, we're gonna skip that because we don't want to revisit it. Otherwise, we're gonna go through all the possible weight, and then we're gonna copy all the weight of the current to its neighbor, and also plus the current edge. So that's how frequent of the neighbor is calculated. And then we're gonna recursively visit neighbor with the parent set as current. And then we're gonna start at root 0 with the parent of negative. And after doing that, all the frequencies and depths and parent will be calculated. Then we're gonna write our LCA AB. Have mentioned in the solution overview is gonna help us calculating the answer efficiently. So the way that we're gonna do it, first, if the depth A is greater than depth B, means they don't have the same depth, then I'm going to reverse it. So we'll make sure A will always having the depth smaller or equal to B. So now I'm going to check the difference, these two nodes. Remember, the node B will always have a depth or equal to A because of check in line 49. So this won't be negative. And then I'm going to B, which is having a higher depth, diff time to make equal in terms of the depth. And if A is equals B, it means that A is the parent of B. So we just return A because that's the lowest common ancestor that we can get. Otherwise, we're going to do a binary search to find the first common ancestor. So we're going to check for the mid and kth parent of A, and also get the kth parent of B where K is set to mid. And AP is equal to BP, then it is a common ancestor of both of them. And this temporary result will set them to AP or to BP, doesn't matter because AP is equal to BP. Then we're going to go lower. We want to find the first common ancestor. So this is one of the ancestors, this is common, but we want to find the first one. So we're going to try to see if there is more that's matching. So otherwise, we will to check the higher to see if there is a common ancestor over there. So after all is done, then we're going to return red, which is the lowest common ancestor of A and B. So with that out of the way, then we can start calculating our answer. So first we're going to initialize answers to an empty array. And then for each query, so first we're going to find the common ancestor of A and B. So A to B length is the from root to A plus the depth from root to B and minus the depth from root to L times 2 as we explained in the solution overview. And the max frequency can be calculated in a similar manner, but we're just going to iterate every possible weight again because there's only 26 of them, so we can iterate it. So we're going to calculate the frequency of this particular weight I using the similar formula that we have seen in line 71 for calculating the depth, but this time we want to calculate the frequency. So the frequency of this weight I is the frequency of this from root, and also this frequency of B from root, and minus the lowest common ancestor from root to L and times 2. So basically the same reasoning behind line 71, and this curve is the weight from A to B where the label is I. So we're going to consider that to see if that's the maximum frequency, and we're going to try every possible weight. And after that, this current answer is just the length from A to B minus the max frequency, because obviously we want to choose the max frequency as the target and set all the remainings to this max frequency label. So that's why we can just do B length minus max frequency. And after doing all that, then we can just return the answer. And that's pretty much all. Let's try to submit that. Okay, accepted. And thank you so much for watching, and I will see you next time.